Okay, let's dive in. We are closing in on the end of our open challenges in evolutionary robotics. We will finish that up today with a discussion of Twitch Plays Robotics, and then we will move on to the second last theme of the course, collective robotics. If you're a robot or an organism and you can't do something on your own, bring in your friends and find a way to cooperate, coordinate, work together, and so on. Okay. You're starting in on deliverable 3, which for some of you might be rolling back your code to assignment 10 and then moving on with a third easy assignment. Some of you are moving on to the third baby step of one of the hard assignments or one of the assignments you came up with on your own. Any questions, comments? Everyone's an expert at PyBullet now, hacking and patching. Okay. Okay. So we were going to talk about Twitch Plays Robotics last time. We didn't get that far. We started with the discussion of language, because if we're going to try and lower the barrier to entry for evolutionary robotics, to bring in large numbers of people to collectively train or evolve our robots in some way, they're probably not going to be writing code or writing fitness functions. The easiest, most obvious way for large numbers of people to interact with large numbers of evolving robots is language. We saw last time a couple of connections between many of the things we've already been talking about, embodied cognition and language, and we ended last time with the embodied metaphor game. How many more did you come up with after we played last week? There's lots of them, right? Okay. Still a hypothesis, still a lot of unanswered questions here about what exactly this connection between the body and language is. But we're going to assume that there is such a connection and try and use the connection between a robot's body and attempts for it to start to understand natural language. Okay, here's the idea. Imagine we have a robot with pressure sensors in its feet, so not that different from what you have already. This robot does not understand any language at all, let alone English. As it's moving around in its world from time to time, depending on its gait, all 4 feet leave the ground just by chance. And at that moment in time, the robot, quote unquote, hears JUMP. I'm going to spell out these words just as a mental reminder to us that the robot doesn't speak English. It hears these 4 squiggles, JUMP, whenever all 4 feet leave the ground. The robot continues on in its way. The next time all 4 touch sensors or pressure sensors drop to 0, it hears the same 4 squiggles, JUMP. A robot that is paying attention might be able to gradually detect a correlation between its body or its body's relationship with the world as reported by the touch sensors and this particular set of squiggles. This is an idea that's been around in robotics for a long time, and it's known as grounding symbols. We've got a bunch of symbols here, JUMP, which are being grounded by the robot, assuming it starts to learn this relationship between touch sensation and these symbols. It's going to start to ground these symbols in the soil of sensor motor experience. If a robot was able to learn this relationship and you were to quote unquote ask it what JUMP means, it might not be able to generate language, but it can show you. It would move in such a way as to minimize touch on all 4 feet. Does the robot understand jump? Yes? Okay. A few yeses. Any no's? Is there anything unsatisfying about this definition of meaning or of understanding?
Doesn't really involve some intuitive sense of height meaning.
A sense of?
Gaining height.
Gaining height? Okay, maybe, right? So for us, jump maybe means, maximizing verticality. The robot could leave the ground and say, that's jump.
That'd be a little unsatisfying because it's like it understands the command and it does something when you give it that command.
Yep.
But like it still doesn't like speak English.
It doesn't speak English. Okay, so we are different, right? We understand jump in a different way. Always a triggering phrase, right? Maybe yes, maybe no. Has been in robotics for many years and remains a hypothesis. This is one way in which you could go about learning language. For those of you that follow the machine learning community, there was a big hustle and bustle last week about GPT-3, which seems to be doing a much better job of understanding language. You can type in an English sentence and it will draw a picture for you representing what you said. It's another interpretation of understanding language. These two schools of thought continue on, trying to build machines that understand language in a non-embodied or an embodied way. In this course, of course, we're going to look at this embodied approach to grounding symbols. Did we mention the symbol grounding problem before? I'm not sure whether we mentioned that. The symbol grounding problem comes up when we talk about the Chinese room. So you've got a whole bunch of squiggles, and the definition of each squiggle is written in a whole bunch of other squiggles. If you're a machine that doesn't understand language and you're trying to understand what a particular word means, and the definition of that word is written in other words, and you don't know those words, there is this sort of idea of circularity. You don't really understand language because you go around and around in circles. Any one symbol is not grounded because it's defined by other symbols which themselves are not grounded. You can find relationships between symbols. We actually saw this when we talked about the Psych project. The Psych project believes that the path to language is just that. If you understand enough relationships between symbols like BILLCLIMTON and other sets of squiggles, that's enough. You'll eventually, if you learn enough of these relationships, you'll eventually create a machine that passes the Turing test. It'll have a conversation with you where you won't know whether on the other side of the terminal it's a human being or a machine. For others like us, for others who work in embodied cognition, it doesn't feel like those symbols are grounded. So we attempt to try and ground symbols in the soil of sensor motor experience. Yeah. In this cartoon example here, motoric words that seem to have a very close connection to the body, like jump or pick and lick and I forget the other one. Pick, lick, and kick, talk, grasp, walk. These are all motoric words. They light up the motor strip. They have an obvious connection to parts of the body. Socialism is not really a motoric word, right? It's not obvious to me which part, if any, of the motor strip that very abstract word lights up. So grounding motoric words, you can see how that might work. But grounding less and less motoric words seems tricky if we're taking this embodied approach to trying to understand language. However, imagine if we're starting at the bottom of this hierarchy. We have our robot that's learning this relationship between particular sensory signatures and jump. It starts to detect other relationships between move. For example, whenever its accelerometer is non-zero, whenever it is moving, it hears the squiggles MOVE. It finds other sensor motor relationships between forward, back, turn left, turn right, turn, and so on. Imagine it starts to learn all of those individual connections between how it moves or how it feels and those motoric words. And then it starts to realize that all of those relationships, it also tends to hear this word mentioned along with these. So if a whole bunch of humans are saying that's jump, that's forward, that's back, and at the same time the humans are also saying jump is an example of movement, forward is an example of movement, back is an example of movement, left is an example of movement, right is an example of movement, the robot might start to ground this slightly less motoric word in these grounded terms. It doesn't hear movement whenever it hears the terms stop, halt, stay still, lie down, don't move, and so on. So it might start to learn that there is a general class of things a wider range of sensor motor experiences, a whole bunch of them that relate to MOVEMENT, and a whole bunch of others that relate to NO space MOVENT. You could imagine that if the crowd is paying attention and they are sending out words to the robot at proper times, the robot might be able to ground increasingly more abstract terms in more grounded terms. This is a very aspirational slide. I don't know whether a robot would be able to actually continue this trick and ground words like political movement and socialism. They seem like very abstract words. It's hard to see a connection to the body. But thinking about thinking is misleading. Let's take another term. Let's take another political movement. So socialism is one political movement. Think of some other political movements. Although they're abstract terms, some of them might actually be groundable. They might actually light up the motor strip. Imagine we put a human subject in an fMRI machine and we just read off to them the names of various political movements. Socialism seems hard to see how that might light up the motor strip. Can you think of the word for a political movement that might light up the motor strip? Think about the embodied metaphors we talked about last time. You take a vote on something and there's a split vote.
Maybe like a sit-in.
A sit-in. Okay, yeah, that's a great one. Yeah, absolutely. Maybe you're willing to be uncomfortable or suffer a penalty or some pain in order for your political ideals.
A walkout.
A walkout. Yeah, okay, getting the idea. If you put someone in an fMRI machine and you mention words like split vote, democracy, Democrat, Republican, it turns out that the motor strip does light up. Which part? What do those collections of terms seem to suggest? Turns out it's the hands. Tricky, huh? Thinking about thinking is very misleading. Yeah, it's not for violent reasons. That's an obvious conclusion. It is about struggle, though, the class struggle. Here's another one. You ever play tug of war? Two teams, right? One team is making progress. You literally feel the fact that you're on the losing team. Things start to switch and you start to pull in the other direction. Voting, split votes, the bicameral system, two parties in opposition. A lot of that actually lights up the motor strip. We mentioned George Lakoff last time in his book, Metaphors We Live By. One of the primary metaphors that he explores in this book as an argument as warfare. Push and pull, gains and losses. Okay. All right, bit of a tangent. Let's focus, today we're going to focus on just very motoric words. And we're going to see whether we can create a software system in which the crowd can help the robot collectively ground a motoric word or a few motoric words in its own sensor motor experiences. Okay, here we go. We're going to do that using the Twitch Plays Robotics project. I think everybody's heard of Twitch, right? Somebody live stream a video game, everybody else in chat comments on how terribly they're doing at playing the game. There is a set of channels called Twitch Plays, where instead of writing commentary into chat, you can type stuff into chat which influences the game character. So no one is actually, the crowd is collectively playing the game. 5 years ago, we created and launched Twitch Plays Robotics, where when you arrive at our particular Twitch stream, whatever you type into chat influences how the robots are behaving. I'm going to walk you through this experiment. It's got 4 parts: act, observe, learn, and predict. Let's start with action. So this was a project actually set up by somebody who took this class 6 years ago. They did a mini version of this for their final project. They joined me as a grad student after this course, and they continued on with this as their PhD project. At that time, we were simulating robots in the Unity physics engine. So we create a simulation of evolving robots. We stream that simulation to Twitch, and we then capture back from Twitch whatever the crowd types into chat, and we store that in a database. Yeah. So this is the act part. We're going to have a whole bunch of robots that are acting and eliciting responses from the crowd. I'll switch and show you what this looked like 5 years ago. This project is still ongoing, so if you visit Twitch Plays Robotics today, you'll see something very different. Here's the interface, and you may or may not be able to read this. So we've got some tutorial panels here on the right in the stream, trying to explain to the crowd that there are two different kinds of things you can type into chat. You can type in commands, plain English words that you want the robot to obey. And you can also supply reinforcement. Where reinforcement here is going to be either yes or no. Yes, the current robot is obeying the current command that we've issued to the robot, or no, the robot is disobeying the current command that we've issued to the robot. Can everybody read the text in this screen in the back row, or shall I read it out to you? Can't read it. Okay, so at this point in time, what you're seeing in the stream is 12 people in chat at this moment in time have collectively voted for crawl forward. So 12 people have typed in over the last 5 minutes or so. 12 people have typed in crawl forward. This is them voting to say, we want to try and teach the robot to crawl forward. 8 people at this point in time have entered the command new robot or riot, because at this point the crowd was getting bored of seeing the same robot over and over again. What even is this? It's so close. Somebody else didn't understand what was going on. So you've got the crowd, as always, on the internet, you've got everything under the sun. Okay, so I'll start up the video in a moment and talk you through it. At this point in time, there's a short pause from trying to teach the robot one command to the next one. So at this point in time, if I unpause this, we should be able to see that in a moment the robot is going to be, sorry, let me skip ahead a little bit. Okay. At this point in time, the crowd voted over the last few minutes for the command walk forward. So we have issued this command, walk forward, to the robot. The robot hears the term walk forward. This is the violet robot. So let me back up again here. Put up your right hand if you think the robot is walking forward, and put up your left hand if you think the robot is not walking forward. We'll play Twitch Plays Robotics. Okay, mostly left hands, right? So as you can see in chat, the crowd agrees with you. Most people are typing in VN. The violet robot is not walking forward. Yeah? So we're collecting commands and reinforcement signals. Let me speed this up a little bit. At this point, there's votes to teach the robot walk forward next. So the crowd wants to keep working on walk forward. And there were a couple votes for spin and probably something else. New robot hype. They're getting bored of seeing the same robot over and over again. Okay. We ran this initial experiment for a couple of weeks. We had 424 separate human subjects come and type something into chat. They were free to try and teach the robot whatever commands they wanted. What commands or what plain English words do you think they typically tried to teach the robot? Walk forward was popular, but so were some others.
Like walk, jump, maybe like the crawl.
walk, jump, crawl. You're going to see that quite a bit. So one of the first observations from this experiment was that the crowd tended to instinctually converge on short motoric phrases, not walk 3 meters in front of the red line that's behind you and then look at the camera. That's, in theory, that's a command you could have tried to teach the robot. That didn't tend to occur.
I just have like a clarifying question.
Sure.
So were they allowed to type just like whatever they wanted? Like how did you validate like their input and then like pick which ones actually like had votes?
Absolutely. So how did we validate their input? We definitely had some filters in place at the time. What were some of the most common English words you can imagine were typed in? Wasn't jump, wasn't forward, wasn't back. What's that?
Knowing Twitch.
Knowing Twitch, exactly. Knowing Twitch. What are the common words common English words you can imagine showed up first?
A lot of cuss words, probably.
A lot of cuss words. I thought I knew every swear word in the English language. Absolutely not, right? You have a friend visit from a foreign country, they're learning English. What are the first 6 words you teach them, right? All the bad words. Same thing here. Luckily, Twitch has kind of woken up over the last 5 years. There's a lot of good cuss word filters that we can turn on and we don't have to do it anymore. We spend a lot of time writing cuss word filters, absolutely. Okay. One of the surprising things, again, we'll look at it in a moment, is not the most popular word, but among the top 10 were short, motoric, non-cuss words that it turns out that the robots were able to learn. We got a long tail. We got a large number of rare commands that people typed in. One was be yourself. I always thought that was an interesting one. Is this robot being itself? I guess so, right? What else can you be? That one is actually very a profound, philosophical, seemingly abstract term, but maybe it can learn the literal interpretation. Somebody else typed in solve Fermat's last theorem. Our robots haven't been able to ground that one yet. No? Okay. A lot of interesting social dynamics. In the first week we ran the experiment, we were obviously watching chat. And we had a couple people show up during the day and say, what is this? And they started to figure out that this was a scientific experiment. They said, okay, come to this subreddit at midnight Eastern time, and we're going to organize. So, of course, the scientists, we went to that subreddit at midnight, and this group came up with 6 cuss words, and they said, we're going to teach the robot these 6 bad words in the following way. Whenever we go to the stream and we type in this bad word, give a yes if the robot moves forward and give a no if the robot moves backwards. For this second bad word, whenever the robot moves backwards, give a yes. Whenever it moves forward, give a no. So this group clearly understood what we were trying to do and came up with spontaneously came up with a collective action to how to help this robot ground the words, but not the right words for the right meaning. We thought it was brilliant. So they organized, they said, show up on the stream at this time at night. The scientist will probably be asleep, not realizing that, yes, the scientist is asleep, but the grad student is definitely not asleep at that time. So Joey, who worked on this project, she stayed up late and wanted to see what would happen at that time. And of course, this is exactly what happened. Some other people were on the stream at that time, who became known as the good guys. They realized what was going on, and they organized to say, whenever a bad guy types in this at this time of night, type in this. When the bad guys type in this, type in this. Fascinating. It didn't actually end up helping. I think they kind of canceled each other out. But yeah, like the internet or Twitch, you get all sorts of behavior. Okay. So despite all that quote-unquote noise in the system, it turns out that the robot there were enough human teachers that provided a consistent enough signal for words to mean what you think words would mean, that the robot was able to ground one word, and we're going to see that in a moment. Any questions before we move on?
Are the results, like, it seems like the simulations are pretty short, at least out of this video. Like,
Yep.
Would the feedback to the neural network or whatever was controlling them affect, like, the next time the blue robot came around?
Yeah, great question. So we haven't got into the details yet. We kept it simple in this first experiment. Remember, there's 4 parts to this experiment: act, observe, predict, and learn. So the prediction and learning didn't happen until after the stream. What you're actually watching here is a bunch of random controllers. We're recording all of those random controllers. We're going to play them back on the robot later. At the moment, we're building a data set, which is controller, robot, word, and crowd response. And I'm going to walk you through the data in a moment. So what the crowd says is actually not influencing the robots in real time. Now, the one that's running at the moment, if you go and type something into chat, that is influencing the robot in real time. So this is actually an example of offline learning, for those that are familiar with this term. We're not going to do the learning online while the crowd is interacting with the robots. We're going to do the learning offline after the fact.
Can you also process some of it and then filter it out?
Exactly, that's right. So we're going to process this data pretty heavily for obvious reasons by now. Any other questions before we push on? Okay. Okay, here's what the data set looks like. In this initial experiment, we worked with just 2 different robots, R0 and R1. R0 was the simpler worm robot you just saw, and R1 is the quadruped. So one of the questions Joey had when she was working on this project is, does the body of the robot facilitate or obstruct symbol grounding? Meaning, do certain bodies make it easier to understand what JUMP means than other bodies? So she wanted to test these 2 different robots. As you just saw in the stream, it ran 24/7 for a few weeks. And every once in a while, when one of these 2 robots was on stream, someone would type in a command, and we would record that command and associate it with which robot that command was typed under, which would give us CIJ, the Jth command that was issued to the Ith robot. This little cartoon example here, there were 140 different commands that were typed in under R0. Multiple instances here can be the same command, so these are not unique commands. C3 could be jump, and C17 could also be jump. People could type in or vote for commands that were sent to the robot multiple times. Okay. When the crowd voted on a command and it was quote unquote sent to the robot, that command would be in effect for about 5 minutes. And over that 5-minute period, we would run a whole bunch of random controllers, N for controller. We'd run a whole bunch of controllers on that robot under that command, which gives us another data set, NIJK, where NIJK is the kth controller evaluated under command J, while robot I was being controlled by this controller, CIJK. Ith robot, Jth command, Kth controller. All of these controllers, each controller is just a set of random synaptic weights. No evolution yet, no learning. For each one of these controllers, as you just did, the crowd voted, and we collected the number of yes votes. It's just an integer. How many yes votes? And we stored that in SIJK1, the number of yes votes that this controller received when it was running this robot under this command, and SIJK0, the number of no votes that the crowd supplied to this controller when it was controlling this robot under this command. That's our data set. So far, so good? Okay, so that's step 2. We're observing or collecting back all of this data as these robots are acting randomly on the stream. Okay, here's an overview of what this data set looks like. As I mentioned, 424, we had several thousand people come and observe the stream, but only 424 of them typed something into chat. Over that 2-week period, 57,000 simulations were run. So 57,000 random controllers ran on the robot. However, there was at least one person on the stream for 6,388 of those simulations, and we got a total of over 16,000 pieces of chat. Remember that people could type in commands or reinforcement. We had people type in almost 9,000 commands. On average, each human subject in this study typed in on average a little over 21 commands. So some people would come, type in no commands at all. They would just type in yeses or nos. A few people would type in jump or solve Fermat's last theorem and then leave again. There are a few people that typed in commands over and over and over again. Okay. Among this set of 9,000, there were 266 unique strings. The most common one, we filtered out the cuss words here, the most common one was jump that was typed in 385 times. So the crowd voted to try and teach the robot JUMP 385 times, walk forward 58 times, 41, and so on. So this is just looking at some terms from the top 10. If you look at the top 20, the top 50, they tended to be short motoric terms, which was promising. Part of this study was sort of an exploratory study to see whether you could actually attract enough people to consistently try and teach the robots plain English. Aside from the cuss words, this was some evidence that this might actually be possible. We didn't tell people to type in short motoric terms, let alone tell them what a motoric term is. Why do you think that happened? People could have typed in, please try and go forward, turn around 3 times, then sit down, and then come back again. That tended not to occur very often.
Be a couple things. People might want to type out the commands quickly on their end.
Absolutely, right? This being Twitch or the internet, people tend to like shorter things. So that explains shorter things. I mentioned be yourself, which is relatively short, not strictly a motoric term. That showed up, but not very common. So what was common was short and motoric phrases.
I feel like instinctually, like you want to see results if like you were the user, and so like if you type in something long and like that like the robot wouldn't be able to do, it just wouldn't make sense. So you're like do something that the robot like could possibly do, which is short, probably motoric.
Bingo, right? Instinctually. Somehow instinctually humans know that go forward, turn around 3 times, sit down, and then come back. The robot's probably not going to learn that. Jump? Probably yes, right? This is actually a very profound idea. Why is it that this is so instinctual? It seems obvious to us, right? Thinking about thinking is misleading. Why does that seem so obvious, intuitive? If you were to play this game and I hadn't told you the punchline of this game, that you might have done that.
I feel like it kind of goes along with you wouldn't teach a baby to run before it crawls.
Absolutely, right? So instinctually, a baby or a young child, you're not going to say, hey, baby, go forward, turn around 3 times, sit down, and come back again, right? Sit up, jump, stand up, stay still, no, bad, don't touch, right? Very short motoric terms.
I feel like most people's experience with training anything is probably like starts with like dogs or pets, and most commands you teach a dog are like one word and like fairly motoric most of the time.
Sit, good dog, right? Short motoric terms. Humans are natural teachers without formal training for good reasons, right? Our ancestors did better if they were able to train our helpless young. For reasons of our physiology, it takes a very long time for humans to be able to grapple with the world on their own. We train them using language to do so. We do so with our pets. Presumably our ancestors did that with our pets as well, right? So there are evolutionary pressures at work in us, or that resulted in us, that makes it feel that it's instinctive or intuitive to train things with short motoric terms. That was another one of our hypotheses going into this experiment, that if we created the right kind of interface, without explicitly saying, imagine this as a pet or think of this as a helpless human child, that people would instinctually respond to the system in that way. Okay. Okay, so now we're going to move on to step 3 of this experiment. Given the fact that people did what they were supposed to be doing, and assuming that people were honest, that when the robot actually JUMP'd, people typed in Y, and when the robot did not JUMP, people typed in N. We don't have evidence for this piece yet. We have evidence for this piece, that they type in short motoric terms. Can the robot learn this relationship? Is there a relationship between the sensor values arising in the simulated robot and the crowd's reinforcement here? So let's have a look at how this works. We took, in this case, we focused on just one command. We took all of the controllers that were evaluated on both robots, the worm and the quadruped. Whenever the crowd issued JUMP, we took all of those controllers. We replayed each of those controllers on the robot. And for each of those controllers, N, I, J, K, the kth controller run under command jump. Here, J equals jump. And on the ith robot, we constructed a matrix T here, which is going to capture all of the touch sensor values generated by the robot when it was controlled by the kth controller. In the case of the worm, it's got 3 links here, these 3 body segments. There's a touch sensor in each of these 3 segments. So in the matrix, we have 3 columns corresponding to those 3 touch sensors. Each row here is going to correspond to 1 time step in the simulation. I can't remember how many time steps we ran per simulation. Let's imagine it's 1,000 time steps. We'd have a 1,000 by 3 binary matrix, where a 0 represents that particular link in the robot was off the ground at that moment in time. A 1 is going to indicate that particular link was on the ground at that time step. So far, so good? Okay. We are then going to compute for each controller 2 more variables. I'll just, keep this brief, I'll refer to them as S0 and S1. We mentioned S0 and S1 already. It's the number of yes votes and the number of no votes attracted by the kth controller at that time. We're going to take S0 and S1 and compute a new value O. On the denominator here, we're going to sum the total number of yes votes and the total number of no votes. So how much total reinforcement did the crowd give that controller under the command JUMP? And the numerator, we're going to subtract the number of no votes from the number of yes votes. What's the range for variable O here? Sorry, wrong brackets. What's the range of values that it can take on? S0 and S1 are positive integers, the number of yes and no votes respectively. We're dividing by the total number.
Is it 1
Minus 1 and 1, right? So if the robot is controlled by a given controller and it sort of shuffles and stays on the ground, and we get back 8 no votes and 0 yes votes, O will be minus 1. The crowd was unanimous in negatively reinforcing that controller under the command JUMP. The robot starts doing the Pepe Le Pew jumping or hopping. We get back 14 yes votes and 0 no votes. The O for that particular controller is 1. What does an O of 0 represent? A tie, or nobody voted. We're going to filter out all of the controllers. We're going to filter out all of the K from this set of K controllers. We're going to filter out all of the ones in which jump was issued to the robot, but there was no one on the stream, or at least nobody typed in any reinforcement. So an O of 0 is going to represent a split vote. it got 9 yeses and 9 nos, or 23 yeses and 23 nos. Doesn't really matter how many. The crowd was in disagreement as to whether the robot was jumping or not. Yeah? Okay. Here's a visualization of what this data is going to start to look like. So Joey, who worked on this project, before we actually really tried to train the robot, we wanted to see if there was any chance that we could train this robot to ground these symbols. So Joey gave the worm robot here a bit of a hint. She took each controller that received at least 1 vote under JUMP, and I don't know, we've got several hundred of those controllers here. Each green circle represents a single random controller run on the worm robot under the command JUMP. For each of those controllers, Joey took T, that matrix, and she marched down the rows and computed all of the rows in which there was at least, she computed all the rows in which it was all zeros. The robot was off the ground at that time step. And computed the proportion of those all 0 rows against all 1,000 rows, which gave her back the proportion of time, it's the other way around. The proportion of time that the robot spent off the ground. If you invert that, it's the proportion of time that the robot spent on the ground. Sorry, it's too many double negatives. She marched down the rows, computed the number of rows in which there was at least 1 1 in that row. At least one part of the robot was grounded on the ground at that time. What is this controller doing? We'll just worry about the horizontal position for a moment. What did this controller cause the robot to do? Spend almost all of its time on the ground, right? It might have left for a few time steps, might not even have been visible to the crowd. This controller out here caused the robot to spend less than half the time on the ground. Yeah? Okay. The vertical axis is reporting O, which is ranging between -1 and +1. You'll see that most of the dots had an O of either -1 or +1. Most of the time, the crowd was unanimous in whether the crowd thought the robot was jumping or not. Why do you think most of our O values were 1 or -1? Why was the crowd unanimous most of the time?
It's pretty easy to tell that if the robot jumped or not, so it'd be hard to have split decisions on that.
JUMP is a short motoric term. Assuming that you're playing the game honestly, most people are going to be in agreement. There is also a twist here to remember that this is a Twitch channel. So most of the time there was maybe 1 observer and 1 person typing in reinforcement for a given controller. And by definition, I don't even know whether an individual is allowed to type in a Y and an N for the same robot. Most of the time the person is in agreement with themselves, right? A single yes vote will give you an O of 1, and a single no vote will give you an O of -1, right? So most of our data here lies at the 2 extrema. Yeah? Not all of it. There was some disagreement in here. Joey took the straight dash line that you see here, and she linearly regressed this line against the data. It's not a very good fit. There is no straight line that's going to approach or be very close to all of these points. But there is enough data here that you can be confident in the slope of this line. And the slope is negative. What is this negative slope telling you? This is the learning part. We're regressing or learning this line to try and fit this data.
That's like the more proportion of time it's spent on the ground, the more likely it is to get like an O value of -1.
Absolutely. Generally speaking, it's not a clean relationship, but generally speaking, the more time the robot spends on the ground, the more no votes it's getting. Less time it spends on the ground, the more yes votes it's getting. This is looking pretty promising, right? This is our intuitive understanding of jump. If I were to start doing random things at the front of the class and you started doing this, my understanding of jump, if I didn't know what JUMP meant, is that whenever I felt the soles of my shoes dropping to 0 against my feet, I see a whole bunch of these. Whenever I spend time on the ground, I see a whole bunch of these. So the robot here is able to ground the symbol JUMP successfully in the soil of its own sensor motor experiences. Everybody see that? Questions? Okay. Joey did the same thing with the other robot. Here are all the random controllers that were run on the quadruped. It's got 4 touch sensors in the 4 feet. She calculated again for the several hundred controllers run on the quadruped under JUMP. Same thing, fraction of time spent on the ground. And how did the crowd tend to respond to these controllers? How did this robot do? Does it understand jump?
Looks like they were in disagreement more. Looks like there's more about is 0.
Could be. Yeah, it might be. Hard to tell. Could be. Maybe there's a little bit more disagreement here. Other observations?
It looks like it spent more time on the ground. Is that
Spent more time on the ground. Yeah, exactly. I'm sorry these graphs are not exactly the same shape, but generally speaking, this larger, heavier robot spent more time on the ground. Does that matter in this case? Did it affect its ability to ground the symbols JUMP in the soil of its own sensor motor experiences? It's the same line here. We're still getting this negative slope, which makes sense, is what you would hope to see, right? If I flip back and forth, have a look at the y-intercept of both dashed lines. It's different. So the slope is more or less the same, not quite, both negative slopes, slightly different negative slopes, and slightly different y-intercepts. What does that mean? What does the fact that the dashed line is different for these two different robots mean?
Maybe like the trigger point and the threshold for what it might learn to be a jump might just be a lower or higher portion of time grounded depending on which robot you're talking about.
Okay, the threshold at which it might learn this relationship might be different. Or distinguish between the two. It might be a little bit harder for one of these two robots to actually learn this relationship than the other one.
Like both of them might call point 2 a jump, but whereas one might be very certain at point 5, this one may still hesitate.
Yeah, true. So you mentioned a threshold. So the robot could take this dashed line and it could say, all right, everything to the right of this point, I'm going to assume is not jumping, and everything to the left is. The robot hasn't done that yet. It hasn't actually determined what is and isn't jumping. It's learned JUMP is a continuum. It just says jump means the following. There are all these things I can do, all these things I have done. I've done several hundred things, and I get kind of different crowd response to those things, but there's a gradient. Things towards this side are more jump-like, and things to this side are less jump-like. You're right, the robot could move on from that and start to make distinctions, but we haven't got there yet. Yep.
Yeah, I think it's a little like misleading looking at this graph too with the proportion of time grounded, because just because it spent almost all of its time doesn't mean it didn't jump once. I think it's kind of like hard to see that.
Absolutely, right? So part of the tricky thing here is, does this align with your understanding of what jump is, right? Imagine the robot stayed on the ground for 999 time steps, and at one time step, which you were able to see, it left the ground. There was a flight phase for just one time step. Is that jumping? Right hand up if you think that's jumping, left hand up if you don't. No hands go up. Okay. Couple of lefts, couple of rights, right? Thinking about thinking is misleading. Jump seems like the most obvious term. It's easy to know what jumping is. When you get down in the nitty-gritty of trying to teach a robot exactly what jump is, it's difficult, first of all, because not all humans agree on exactly what jumping is. Yeah? It's a part of what makes language so difficult. It's hard to get the robot's understanding of jump to align with our understanding because we are not necessarily all aligned in what it is. The other thing we saw very common in chat was someone would type in, yes, the robot is moving forward. Someone else would type in immediately N. The first person would say, are you crazy? That was moving forward. Why did you say no? This person would say, that wasn't moving forward. It only moved this much, or the back part of its body never got in front of the red line. An argument would break out about what that term actually means. Kind of interesting, yeah? Okay, we'll come back to that in a moment. The other thing that's interesting about this, I think, is because these lines are slightly different, even in this admittedly screamingly simple case, these two robots, assuming that you are willing to accede that this is the robots understand jump, they understand jump in a slightly different way based on their bodies. So there is not perfect alignment between these two robots as well. If they were able to speak, the worm might say, yeah, this is jumping, and the quadruped might say, no, that's not jumping. There is a big problem in the AI field that we haven't talked about in this class, which is the value alignment problem. You're trying to teach an autonomous car to drive safely. You show that car a million images of what lies in front of it on the road, and you ask the crowd, yes, this picture indicates that the car can safely move forward, or no, that image represents a case where the car should slow down, there's danger ahead. Turns out, if you do this in reality with a million images taken from the dash cams of cameras, humans don't agree. So what are we supposed to tell our autonomous cars? Yeah? The value alignment problem, getting machines to see the world and understand the world like we do, very tricky. In theory, you would like an autonomous car at every point in time to say, the current image or my current understanding of what I see, if I showed that image or that short video clip to a million human beings, I would get back an O of 1. Those million human beings would all say, that's a safe environment, go ahead, move forward, right? That's what you would, if you had a perfectly aligned autonomous car with us, that's what you would get, yeah? Gets even more complicated than that. Turns out that if you show a whole bunch of people tricky situations, the car is now in danger, it's sliding on the road, there is a pedestrian nearby, there's a passenger in the car, and there's a baby in the back seat of the autonomous car. What should the car do in that case? There are multiple human lives involved in that moment in time. If you show that situation, you present that situation on the web to different people in different countries will vote differently. You get relatively high alignment within certain countries, but across countries you get lack of alignment. Why? This was the Moral Machine Project. You can go and Google this and check it out. Why high alignment within a given country, but different alignment across countries?
And part of it could just be due to the fact that, like, private transport, like cars, aren't as common in certain other countries, and so they may be more generally cautious just because their experience with cars are much more limited or more different than in other countries.
Yeah, could be. Yeah, exactly. Some of the countries, it was a huge experiment. It's a huge data set, much larger than this. Might be that in certain countries, that might be what's influencing it.
Maybe in some countries, like people walking around like in big cities is much more common than in like rural areas, and some countries might have more cities than rural areas.
Okay, absolutely. So there was disagreement among urban and rural participants in this experiment. That's true. Lots of dimensions along which people can disagree. We're focusing on the countries.
Different countries have different moral beliefs and systems in place.
Absolutely. So when human lives are at risk, people strike different apply different moral calculi, different ways of computing who is most sacrificable in this situation and who should be most protected. Kind of odd, but maybe in retrospect kind of obvious. It is now influencing the global legal frameworks around autonomous cars. Turns out that Google and Silicon Valley can simply not train a neural network and drop that into every autonomous car everywhere in the world, because that neural network is going to strike different trade-offs in dangerous situations. And that neural network may be more aligned with Western, white, male, tech-savvy programmers than others. Very, very difficult. So one of the interesting fallouts from the moral machine experiment is there's probably going to be different legal frameworks developed around autonomous cars or autonomous transport in different countries based on some of these cultural values. So we're trying to stay grounded with short motoric words where it seems obvious what the answer should be. Very difficult to stay at this very concrete level. Okay. All right, back to Twitch Plays Robotics, sort of a smaller laboratory for testing these ideas. In this case, Joey kind of cheated by already telling the robot what jump means. It has something to do with the proportion of time spent on the ground. We want the robot to figure out on its own what JUMP means. So we took this one step further. We have all our sensor data here. In this fifth step of the experiment, Joey created this neural network. It's got 3 input neurons, 1 output neuron, and a total of 4 synapses. Each synapse has its own weight. You can see one of these synapses is a recurrent connection. Joey took each of these T matrices, the touch sensor data for a given controller, and she pushed that matrix through this neural network 1 row at a time. This neural network is not controlling the behavior of the robot. This is, if you like, a part of the robot's brain that is learning to try and relate JUMP to sensor motor experiences. Yeah? We push each of these 1,000 rows through this neural network, and based on these 4 synaptic weights, at the end of that 1,000th update of the neural network, there is a floating point value sitting at the output neuron. Joey trained this neural network to minimize the distance between O prime here, the number output by the neural network, and O, the crowd's response to that controller. If you train up this neural network to take all of those controllers that were executed on one of the 2 robots under JUMP, and if you train these 4 weights so that in all of those cases this distance is small, what has this neural network learned? Every time you plug in one of those matrices, it spits out O prime, which is very close to O. The neural network guesses the crowd's response to that particular controller. What has the neural network learned, if anything? Any ideas? Okay. Let's try and answer this question by taking this to the 6th and final step. We've trained this neural network to try and minimize distance between O prime and O. Joey held out some of these matrices. She didn't actually train this neural network on all the matrices she had at hand. She kept some back. After the neural network was trained, she fed those held out matrices row by row to the trained neural network and looked to see what O prime was. In most of these cases, O prime is actually close to O, which was hidden from this network. The network never saw that particular crowd response for that matrix. What is this neural network doing?
it's training it how to predict how well its synapses work in getting the desired result.
Absolutely. So in this last stage, when we test this neural network, it's predicting. If I move like this and generate this kind of sensor data, although this happened in the past, if I move in this way, I predict the crowd will respond in this way. That's my understanding. That's this neural network's understanding of jump. Yeah? If I understand jump and I ask you to play the JUMP game, I think to myself, okay, I'm going to jump, and I predict that most of you are going to do this. Or in the next second, I'm going to stay crouched on the ground, and I predict most of you are going to go like this. If that's what's going on in my head, and that's what I do, and that's what results, I, quote unquote, understand jump in an embodied sense. Make sense? Okay. Question is, how well did this neural network do? How closely could it output O primes that predict O? Okay, here's the answer. Let's look at the simple robot first. This is the worm robot on the left here. We started with a control. This is like A/B testing. You can think of blue as A, and you can think of green as B. In blue, we took a whole bunch of random controllers and random O values. We generated random O values between -1 and 1. We trained up the neural network on a bunch of those matrices where they're trying to predict random O values. And then we sent it, after training, we sent that neural network a bunch of additional T matrices and a whole bunch of other random values for O, and we measured the average distance between O prime and O, and you get what you would expect, which is, it's not quite 0.5, but it's pretty close. Most of the time, if they're random numbers, you're trying to guess a random number generator, best thing to guess is 0, right? You'll be about half as far away most of the time. Okay. In green here, green is reporting how well the actual neural network did at predicting actual crowd behavior. Still not great, 0.42. On average, there was 0.42 difference between O prime and O, but green was significantly lower than blue. It was learning some part of this relationship. Same thing with the quadruped over here. Green was statistically significantly lower than blue. By training this network, the O prime values that it's spitting out is getting closer and closer to O. Very simple experiment. The robot only had access to touch information, not acceleration, but it seemed to do pretty well. The robot is not just learning about JUMP, it's also learning about people, right? How people tend to respond to this robot under these commands. Okay. All right, that concludes our discussion about Twitch Plays Robotics and language, at least for now. And we've seen the value alignment problem rear its ugly head. Any questions about this before we switch mental gears here for the last 10 minutes? No? All good? Okay. All right, so we are going to start in on the second last theme of the course, which is collective robotics. This is a 3-part lecture. If you are a robot or an organism or a human being, something is difficult or impossible for you to do on your own, bring in your friends. You can figure out a way to coordinate. It turns out that if you have more and more friends, you have a larger and larger team, it gets harder and harder to coordinate your efforts unless you start saying, you over there, you do that, I'm going to do this, you do that. So we're going to explore language again, but now we're going to explore it from a collective intelligence point of view. What are the origins of language? Nobody knows. There's lots of theories. One of the leading theories is it allowed our ancestors to organize better on the Serengeti Plain and do what our ancestors needed to do on the Serengeti Plain. We're going to look at signaling and communication. We are not going to look at language. Language here is something different, just communication and signaling. And in lecture 23, we'll look at another aspect of collective behavior, which is self-replication. If you can't recruit enough friends to help you, make more friends. Literally, make more friends. Okay. In any discussion of collective behavior, collective intelligence, we need to always start with starlings. Anybody seen a starling murmuration before? Beautiful, aren't they? Okay. Obviously, lots of species on this planet, including ours, that have come up with different strategies to work together. Why? What's the advantage of flocking, herding, schooling? No language yet, just collective motion.
Survival.
Survival how?
By making your predators fearful of you by becoming larger usually.
Okay, right? So exactly, startle or confuse or surprise your predators. So for prey, there's very good reasons to organize in groups. What about predators? Is there an advantage for predators to work in groups?
More efficiently take down prey with less energy total consumed.
Absolutely. There are benefits on both sides to organizing in groups. We mentioned coevolution in this course already. If the prey evolved to organize in larger and larger groups better, that tends to decrease the fitness of predators who get confused. They can respond by organizing in groups to combat the groups being organized by the prey. And you get evolutionary pressures between predator and prey groups for both groups to get better and better at organizing in larger and larger groups. And you get starling, sardines, mackerel, buffalo, humans that organize in groups very, very well. What exactly is going on inside these groups? Again, lots of open questions in biology about how animals organize in groups. Lots of theories out there. Craig Reynolds, back in the 1990s, a computer graphics researcher, took one of the simplest possible explanations for group behavior. Reynolds is kind of the counterpart of Breitenberg. Remember, Breitenberg studied fruit flies and how fruit flies find rotted fruit and said, all of these theories are too complicated. Here's a really, really simple theory. And he tried to build that into machines. Same thing with Craig Reynolds here. Craig Reynolds created what later became known as, I'm running out of real estate here, Boids. Here's the original Boid algorithm. You have a bunch of these Boids operating in two-dimensional space. Each Boid, like the green Boid that you see here, has a sensing radius. It can sense all of its fellow Boids that are inside this circle. It cannot sense any of its partners that are outside this circle. The Boid is going to try and derive two numbers. Two numbers. Theta, which direction is it going to head in next? And R, the radius or the length or the velocity that it's going to move at the next time step. So heading and velocity. Yeah? Okay. Each Boid is going to compute three separate functions: separation, alignment, and cohesion. In separation, it finds the positions of its partners. In this case, there are three. Takes the average position of those neighbors and changes its heading to head away from that average position. So separate, turn away from the center of mass of everyone you can see. So this function outputs a change in heading and maybe a change in velocity. Before this green Boid moves, it also computes alignment. It senses the direction in which all of its friends are heading, computes the average alignment or the average heading of all of its neighbors, and alters its heading to line up a little bit more, to align with the average heading of all of its friends. So we have another set of numbers which are voting for a different change in alignment and velocity. And cohesion, which is kind of the inverse of separation, again, compute the center of mass of all of your partners and turn towards that center of mass. If you take the change of headings requested by all three of these functions and change in velocity, sum them together and take the average, that becomes the new heading and velocity for that given Boyd. And every other Boyd in the population runs exactly the same three functions at every time step. Yeah? If you do, you get things that look like this. I apologize for the quality. This is taken from the early 90s. Thinking about flocking is misleading. You might not need something that's very complicated. With relatively simple rules, and those same rules running on every individual in the swarm, you can get some very rich, compelling behavior. Not only do the Boyds seem to flock together pretty well, but they also kind of break into groups and flow around objects. Why? You get that almost for free from the Boyd algorithm here. How?
You can actually separate to avoid crowding, and that can happen around objects, but then you guys, as it kind of reaches around, it coheses when it detects whatever is local, so it kind of depends on what the definition of local flock mates is, but they come around the object and it's close enough, right?
Absolutely, absolutely. We can define our local flock mates to be him or her or it, right? It doesn't really matter. It can be inanimate objects. There is stuff on my right, so I'm going to turn a little bit to the left. There's stuff on the left, I'm going to turn a little bit to the right. And you get some of these behaviors for free. Okay, we've got 2 minutes left. The Boyds was invented back in the early 90s by a computer graphics researcher. Disney picked up on this in 1994 in The Lion King. This is one of the very first uses of CGI in a Hollywood movie. And you get things like this. Still looks pretty good all these years later, huh? You've got some prey in there, some predators that are also moving collectively. The wildebeest flow around this spur of rock. Every major motion picture today where you've got CGI of very large crowds or combatants, it is some version of the Boyd's algorithm at work. Obviously today, the Boyd's algorithm has hundreds or thousands of these functions that slightly influence the members of a virtual crowd. You can alter these so that different members of the crowd have slightly different versions. We're going to stop in a moment, and I'm going to leave you just with this thought experiment. You just saw the original video of the Boyds. Imagine we reran a simple simulation of Boyds, but we removed the separation algorithm. They only used alignment and cohesion. How would the flock of Boyds behave? Same thing, what would happen if we left out alignment? What would happen if we left out cohesion? I'm going to stop here. You have a quiz due tonight. You're working on deliverable 3. Have a good rest of your day.